Hello, can you hear me, Dr. Annaswamy?
Yes.
Okay, that's good. Yes, so I'm gonna promote you to a panelist so you could share your screen and have the other privileges.
Yes.
Yep. Hello. Um, for your information, this is being live streamed on YouTube, and
Okay.
so people will be asking questions on YouTube, and I can relay those questions to you.
Okay.
And Andreas, he's actually going to join on the stream, and he's going to be
Okay.
yeah. So yeah, he wanted to welcome.
All right. Do we start 5 minutes after, or do we start
Yeah,
at?
we can start at 12. Yeah.
Oh, okay.
See, I'll be muting myself for a couple of minutes.
Okay. Sure.
So, thank you. So I think we can get started. Um, Hello, everyone. Welcome back to this week's session of the Data-Driven Learning and Control Seminar series. And Nishant, and today I'm honored to welcome our speaker, Dr. Anuradha Annaswamy. She's from MIT, and before I pass on the mic to Dr. Annaswamy, just little bit about her, and she is the founder and the director of Active Adaptive Control Lab and Mechanical Engineering in MIT. And her research interest spans adaptive control theory and its applications in aerospace, automotive propulsion, energy systems, and as well as cyber physical systems like smart grids, smart cities, and smart infrastructures. And she has received Best Paper Awards at the Axel by 1986 and the CSM Best Paper Award in 2010. And she has had the Distinguished Member and Distinguished Lecturer Award in IEEE Controlled Systems Society and Best Paper Award from the IFAC Journal of Annual Reviews in Control for 2021-2023. And in addition to that, Presidential Young Investigator Award from NSF between 1991 and 1997. And she is a fellow of IEEE and IFAC, and is also a recipient of the Distinguished Alumni Award from IISc Bangalore. And she has authored the graduate textbook on adaptive control. And in addition to that, she has served on the editorial board of very prestigious control journals like Transactions of Automatic Control, Automatica, uh, Smart City Networks, and control of network systems, and in Open Journal of Control Systems, and many more actually. And he has co-edited the CSS report for impact of control technology, and the first editions from 2011 and the second edition 2013. And in addition to that, another CSS report on control for societal scale challenges, roadmap to 2030. And she is currently serving as the president-elect of the American Automatic Control Council, and she will also, so moving on from January 2025, she'll serve as the editor-in-chief of Control Systems magazine. And today, Dr. Annaswamy is going to present on the topic, the role of adaptation in learning, safety, and optimality for autonomous systems. And without any further ado, I'll pass on the mic to Dr. Annaswamy.
Thank you, Nishant. Oh, that was a very kind introduction. I really would like to thank you and Andreas for this opportunity to come and make a presentation to Cornell University, part of the Data-Driven Learning and Control Seminar. Let me share my screen. One second, okay? Hang on one second. I'm sorry. All right. So, all right. So you're able to see my screen? Okay. All right. So it's a pleasure for me to talk to you about the role of adaptation. And what I want to share with you is some of the highlights of what we've been doing in our lab. This work has been sponsored by Boeing and Enforce Research Lab, and a number of people who basically came up with the results that I'm going to share with you, and I'd like to acknowledge all of them here. So what we're all trying, so this is sort of roughly the outline of what I'd like to go over with you. Start with adaptive control, look at the intersection with learning, with safety, with optimality, and talk about a couple of examples. Now, what really unites all of us in here is really a way in which we can analyze and synthesize complex dynamic systems. And so we are always looking at how uncertainties and constraints basically affect these systems, and we can shape them and fashion them in a way so that system goals are realized. And so typically we look at a whole bunch of things in the inner loop, So we want to address issues of stability. We want to address of robustness. And of course, even while we're doing all of that, we want to make sure that it doesn't wander off into regions where they are unsafe. And we want to make sure that all of these things are done very precisely and with minimizing some sort of a cost or time or energy or space or what have you. And we want to be able to do all of that even when there are all kinds of uncertainties that are present that you're trying to accommodate, and you're able to meet all of the different constraints. So we've been doing this for a while, and we always start with water clocks and steam governors as a starting point. And so it's not the idea of shaping the performance of a system is something that is part and parcel of any of the systems that we have designed, and we have always used data in order to really take that forward. And fast forward several decades, and the same principles are what we explored in the impact of control technology report that Nishant mentioned. And so the idea here is to show that these control of physical systems are really not relegated to just a few sectors, but it is really across several domains. And in all of the cases, the success stories are really brought to the forefront. And that was basically our thinking in these reports that we wanted to showcase. And there's a variety of examples that we drew from different kinds of applications. And that's what you see in here. And so we wanted to go on to talk about not just these kinds of sectors where traditionally people have looked at it, but the ones that went beyond and looked at various kinds of smart infrastructures. And all of these are basically providing a nexus between the digital and physical worlds. So and it's not, of course, surprising to see that, the boundary of what controls can do extends far beyond. And so we also looked at how societal scale challenges can be addressed. And indeed, that many of the things that we're doing really sits squarely in the middle of these kinds of endeavors and are integrated with these societal drivers. So bringing the story closer to autonomous systems to say, okay, what is it that we are trying to do? The story between the cyber layer and the physical layer is something that is always ongoing. And so we want to really take a look at what happens and how we can design systems that really deals with uncertainties that may be present when there are some real-time anomalies that can occur that you can't always anticipate. And that basically is the hallmark of what an autonomous system can do. And so the question here is, what is the role of adaptation and how can it really accomplish the design of these, the box that we're talking about in the cyber layer, where we really collect data and make these decisions in real time in order to really deal with uncertainties and constraints that occur in real time as well. So that really is the goal in here. So adaptive control is something that has been looking at, squarely addressing this problem. And just like control systems, adaptive control too has a very long history and spans really several decades. And so the primary way in which this works is really to look at methods by which you can design the decision-making structure in a parameterized manner. And this parameterized manner is basically indicated in the form of potentially some physical parameters that are part of the safety critical structure system that we're trying to control. And we not only design a control algorithm that decides how the control input is designed at every instant of time, but also learn in the process an estimate of whatever is this parameter that might have an uncertainty present in it. And so the real-time correction really comes in the form of a parameter estimator, and that parameter estimator basically learns using data that you collect in real time and whatever prior information that you might have in the form of a model structure. So let me walk you through some specific example. And the way it does that is really to look at it from the point of view of two kinds of errors. And so you look at the model structure and the online information, and all of that gives you something called a performance error. It's something that you can measure and you can reduce, and it's something that needs to be reduced. Whereas the other kind of error that is implicit in it is this is the one that you're trying to get rid of. It is the learning error. And so it is unknown, but because you adjust your parameter estimate, you can basically adjust the parameter error. So how do you design the learning rule in a way so that this performance error is reduced is really the way in which the storytelling happens in adaptive control. So these quantities, the parameter error that you have and the performance error is not always related through a simple structure. It really depends on the underlying dynamics that you have and the underlying kind of complexity that you have in the system. So the error model is the entity that basically relates these two. And therefore, you have to be able to contend with the kinds of complexities that you have in this W of S, which might not even be just a simple dynamics. It can have nonlinearities, et cetera. And so how do you then use all of this, leverage the structure that you have to design the learning rule? And so that's sort of like you could translate the problem of designing adaptive control systems into the goal that I have listed over here. For example, if you have a very, very simple linear regression problem, and even though it's simple, it actually is ubiquitous. It appears in a whole bunch of estimation, prediction, learning, optimization, et cetera, set of problems. And so if you have that kind of a relation, you basically leverage the structure in order to build an estimator. And so in this case, the performance error is simply something comes out very easily. It's just the difference between y and y hat, that the actual output and the estimate that you think it is. Now, the parameter error, on the other hand, is the difference between the unknown parameter that you have and the linear regression coefficient, basically, and what you estimate it to be. So now, in this particular case, it turns out that the relation is this very nice, simple linear one. And so if you think about something like the cost that you're trying to reduce, it actually is a very nice convex function. And so you can simply use the gradient in order to really get to the bottom of the hill. And it turns out that this is really a very straightforward problem. And this is what we call as error model 1 in the adaptive control literature. But the problem is that you can't always do that. Remember, I told you that this is a simple example. And in a real example, you really have a dynamic system. And this dynamic system then becomes it introduces some complexities. And it turns out that if you simply use the same kind of algorithm that you had before, you can't quite do business as usual. Why? Because you don't have this quantity E prime, which is the output of the linear regressor. What you really only have is this quantity E, which between the two, you sits this W of S, which is really very complex, right? So you don't have access to E prime. And therefore, if you use E squared and then use a gradient descent, what was shown was that this actually can lead to instability. And so one really has to worry about how you design a stable learning rule. And this is really the part and parcel of what constituted adaptive control. So what was done is basically to say, no, don't really look at it as a gradient descent problem, but really look at it as something that gives you a stability framework. So we construct this candidate, which could be serve as what we know as very well as a Lyapunov function. And hopefully that becomes an actual Lyapunov function by taking a look at the derivative and designing the parameter estimate, the learning rule, in a way so that it's actually V doesn't grow. It's negative semi-definite. And it turns out that you can do that in a number of cases when you have a certain kind of structure in WFS. And that basically was the one that countered the instability that was discovered in the literature. So this is what we call as a stable adaptive law. And so it turns out that this stable adaptive law coincides with this the simple gradient in this particular linear relationship, because it turns out that the same thing gives you also a V dot that's less than or equal to 0. But the point to really keep in mind is that it's not always going to look like the gradient in general. And that's why you need to have a whole different way of designing the learning rule. So the structure that I showed you in terms of the stability rule and picking a candidate Lyapunov function and showing that it's a Lyapunov function is really what was adopted in the higher order system. So when you have a high dimensional problem where all of the states are accessible, you can figure out the same kind of a procedure by which you derive this error model. And in this particular case, remember I told you there is a W of S, it takes a simple structure. And for that W of S, it turns out that you can actually come up with this particular kind of rule, which really uses the performance error in a very specific way and leverages all of the components that you have to have when you construct this Lyapunov function candidate, because there is, for instance, a P matrix that shows up, which is a solution of a Lyapunov equation, et cetera, et cetera. But without going into all of the details, the big picture here is that here is a learning rule, and that learning rule is something that was specifically constructed using the structure of the dynamic system, yet it is able to come up with a control strategy for dealing with a parametric uncertainty that occurs in real time. That's sort of the story in here. So the same kind of idea can be extended even when all of the states are not accessible. So when you have, say, for instance, just a transfer function, and that transfer function is the one that sits between the input and the output, and it's still linear. Problems are still linear here, except that now you have to figure out a way of stitching together a controller with an observer, and that's what the structure is. And here is the adaptive law that basically looks at the error E, and it collects all of the states that come from this particular observer structure, and that simply turns out to be the answer. The problem becomes a little bit more complicated. I'm not going into all of the details in here when there is more lag between the input and the output, but suffice it to say that one can design these adaptive rules. And you can show that the performance error indeed goes to 0. Now, you can extend the story to when you have nonlinear dynamics as well. And so if you have an unknown nonlinear system that looks like this, then you leverage some structure, and often there is an underlying linear parameterization that sits. And so in that particular case, you can leverage that linear structure in order to design the nonlinear control rule. And you can have the certainty equivalence principle basically carry over, which is that even though you design this feedback linearization with unknown parameters, you simply staple together that control structure with the parameter you replace by its estimate, and that will lead you to the solution. And you can come up with a rule for adjusting the parameter estimate. And when the feedback linearization structure is not available, you can actually leverage. So okay. Before I go to that, certainly here we assume that the phi of x is known, but sometimes that's often not known. But you can sort of see elements of connection to neural networks in here, in that if you have a linear single layer network, that basically is what we are saying is the structure of the nonlinearity. And so if that assumption is valid, then the adaptive rules that I'm talking about here are valid. So there are many other such extensions that people have derived. And that really is articulated very nicely in this book, which was written again a few decades ago. And that basically expands on the notion of feedback linearization and says, even if you don't have that structure, you can use this technique called backstepping that allows you to essentially keep propagating the analysis backwards until you actually design a control system where the actual input shows up, and that backstepping allows you to figure out what that process is by which you recursively keep tweaking your Lyapunov function candidate. So just to give you a very specific example, okay, now that I've told you that there's a theory and that there's a body of work and that it articulated based on some rigorous analytical principles, a lot of which are built on stability notions and, of course, Lyapunov stability. And there are other kinds of stability characteristics that people have leveraged as well. I just want to sort of shift gear a little bit and show you what is it that happens when I actually implement an adaptive controller. So this is the one that I just want to show you a short video, and hopefully it'll play at your end. And so what you will see is a quadrotor. And the quadrotor basically is controlling, you want to hover. And the challenge is basically that a part of the propeller blade breaks. And so that's the real-time anomaly that occurs. And so you want to be able to adapt to it. So I'll start off the video where you'll see a controller that is not adaptive. Are you all seeing the image? Okay, I'm not playing the sound. I don't think it's relevant, but you can see that it crashed because there was basically an asymmetric moment. Now, this is the adaptive one. And so even when the propeller blade snaps, you can see that the way we instituted that was to have this little razor blade pop up and cut a duct tape which basically reduced the moment arm, and that basically led to a roll imbalance, and then there was a yaw as a result, et cetera, et cetera. So you can see that the adaptive controller corrects for it online. It doesn't know when it'll happen, if it happens, by how much the moment arm reduces, but without any of those information available to it, the fact that it's got the state measurements and this kind of a control input and this kind of a learning rule, it does the job. And it is built on analytically rigorous principles, right? So, so that's the kind of performance capability that the adaptive controller has, where this kind of an anomaly is prevented simply because of the software capability. That this is the only difference, that the parameter estimate is adjusted rather than keeping it fixed. So building further on these things, we can then have additional unmodeled dynamics as well. And these unmodeled dynamics basically are things that could happen due to unknown actuator dynamics, either time delay or because of higher order dynamics that are neglected. And it turns out that you can come up with a strategy that still keeps everything bounded and robust adaptive control is possible. And this is through adding regularization or a dead zone, or actually projection works out very well. We can also accommodate input constraints in the form of magnitude and rate saturation. So here, for instance, the main idea here is that all of these adaptive systems basically function in the form of an adjustment in the learning rule. And the adjustment in the learning rule basically is ensured by having a performance error as a target. So the performance error, therefore, is a construction of that is important, and the construction should really be based on things that you can actually attribute to parametric uncertainties, right? So when you have a saturation, the question is that something that you adapt to? Because it's a disturbance, right? It's something that is unintended. So you really should not think or adapt to it, and therefore you should modify the performance error. And that basically is what we did. And so in this particular case, the performance error is modified in some specific way. And when we do that, we actually can do accommodate this magnitude and rate saturation. And not only have we developed all of the fundamental principles for it, but a whole bunch of papers have been written where we explored it in various applications, in positioning systems, in combustion propulsion systems, in aircraft systems, and in all of them, it actually performed very well and experimentally. So for example, here is one where in a propulsion system, there is a phenomenon called thermoacoustic resonance. And the thermoacoustic resonance basically happens because the heat release acts as a forcing function that is in phase with the swing of a pendulum. And so because of that, it really introduces something like a positive feedback, and it basically creates resonances. And that's what leads to this big baseline. You can actually hear these things because these are in acoustic frequencies, and people used to call it a hum or a buzz or a screech, depending upon the magnitude of the frequency. And the real wonderful thing was that when we introduce adaptive control, which is the cyan color curve, and this is an experimental result from an actual Rolls-Royce scale rig, we were able to reduce this. Let me see if that goes away. Yeah, we were able to reduce the amount of acoustic resonance significantly by 30 dB, where the adaptive controller knew absolutely nothing about what the system was doing, and we were able to with no knowledge of the except for the model structure, we were but we didn't know anything about the modes or the actual frequencies that were being driven to resonance. This is the example with high-performance aircraft, where the idea was basically to not only have the angle of attack and the elevator angle basically act as a control input, but we also wanted to make sure that it honors a rate saturation limit. So you can see that our performance basically does generate a solution which really makes sure that the performance is still reasonably okay, but it basically follows the command by keeping to the elevator limits. Because if you don't do that, you're really going to burn out the elevator, and that's something that you don't want. And this is for a high-performance aircraft with high fidelity. And so you can see that something that is physically infeasible is avoided by having our algorithm, which accommodates the result. And this is not the only example. There's been any number of platforms where people have done actual flight tests where adaptive control has been implemented in one form or another. And all of these are, of course, uncrewed flight control applications, and they all have led to improved performance and reliability. So that sort of sets the stage for adaptation can do. So now let's talk about learning, right? So learning has always been part and parcel of any adaptive controller. We've always required that parameters which are uncertain are learned. So it's not a surprise that it's not an afterthought saying, oh, I'm going to do now learning. No, learning has always been a part of adaptive control. And the learning basically occurs in the form of learning the unknown parameter. So there's a theta that is unknown, and that's the uncertainty, and you're trying to learn the theta, right? So this is like what adaptation is all about. So if I wanted to not, so remember that in all problems, if you're going to talk about a parameter that is unknown, and that's what is causing the uncertainty, then there are two separate goals here. You're trying to make the aircraft go somewhere. That's a control task. Oh, you're trying to learn the unknown parameters that basically are part of, let's say, the actuator. That's a learning task. Now, one need not imply the other. And this interplay between what exactly are the conditions that are going to support control and the conditions that support learning are two different questions. And there are sometimes trade-offs. And this is basically what adaptive control has examined over the past 4 or 5 decades, right? So, and it's also very clear for us, why do we want to learn the parameters? Because it gives you robustness, right? Because a small change in a parameter can lead to a huge change in the state space. And therefore, if you want to make a precise real-time decision, parameter learning is important because it gives you robustness guarantees, right? So this is very, very important to keep in mind. And what is also fantastic about learning is parameter learning is that there is a necessary and sufficient condition. So which means that if you introduce this concept, which is persistent excitation, which basically is known as uniform observability, it spans the space, exploration, all of those are synonymous concepts, then you learn the parameters. You cannot learn the parameters if you don't have excitation. So let's just be very clear about it, right? There are no two ways. So for example, if you have a scenario where you have this very simple two-dimensional problem, and the regressor, that the data which is coming from the data is basically something that is at switches between two different directions. Then you have persistent excitation because you have a full rank in this 2 dimensions, right? If you have a 3-dimensional vector and you're still switching between 2 directions, it's not going to be persistently exciting because you have the 3rd dimension which you have not explored. You need to explore all subspaces. That's the idea. So the right-hand side, that figure is not persistently exciting because you're always in one subspace, as simple as that, right? So if that is the case, then the left side gives you learning, the right side does not give you learning. There's imperfect learning with the right side. So something to keep in mind, right? And this is really the same idea of exploration. And if you're trying to really make sure that the transition between your training data and testing data is seamless, you really have to be able to explore all of the different kinds of things. So the fact that I'm talking about necessary condition means that there is also a notion of imperfect learning, right? So this is what I said earlier. Performance, bringing the error down, E down to 0, and bringing the parameter error down to 0 are two different things. And sometimes it can be conflicting, right? And therefore, it's really like if you want to eat at a good restaurant, then you have to once in a while have an experiment where you eat bad food, because that's when you really learn how you can maximize your performance in terms of always eating good food, right? So at that time, when you are experiencing a bad restaurant, your performance does go down. That's what we mean by conflicting objectives. Therefore, an effect of imperfect learning is something that we have to accommodate. I mean, it's fine when we are eating, when it's a restaurant objective, but in a aircraft, you can't have that kind of a deleterious effect on a performance. And so one has to really be sure, right? So here is an example in a flight control where how we can show you as to how adaptive control gives you, even with imperfect learning, good performance. So let's say that there is a particular parameter that you have, and that parameter is the one that will give you the right angle of attack. But then for whatever reason, there is some uncertainty. And because of that uncertainty, you cannot do the same thing with theta 1, but the actual parameter value has changed to theta 1 plus some delta, which you don't know, right? You're trying to learn that. So if you put that in, things can really go bad, right? So if you don't have learning, your angle of attack goes kaflooey, right? You don't want that. So what you want to do is to bring it to something so that you have the same performance. So imperfect learning means I don't know. I can never learn what this thing is, right? So is it possible that even if I don't get to theta star, can I get to some other value such that the performance is almost the same and therefore I'm okay? And that exactly is what happens. Even with imperfect learning, what have you learned the parameter to be? You don't have excitation, right? First of all, excitation is necessary, which means if you don't have excitation, you won't learn, which means that theta 2 is not going to be the same as theta star. So that's imperfect learning. Yet, what we want is the performance goal, which is minimization of the error E, to be realized. And that's what we can show. And all of the designs that I talked about with the stable learning rule and with the Barbalat's lemma accomplishes performance error going to 0, even without theta converging to the true value. Very important to keep in mind. Because if you don't do this, okay, so what are we losing? What we can lose is the goodness of the performance. Whenever you have a disturbance, and disturbances can always be present, so the top row is what happens with imperfect learning. So you can see that, imagine that your world ended at 20 seconds, right? So you have a constant reference input. Then your loss function has gone to 0. Beautiful, right? You're happy. But learning error has not gone to 0. But so what's the impact of that? Well, suppose you have a new step, then your performance error basically jumps, but it does go back to 0 again, because remember, this 20 seconds could be like infinite time. Maybe I just have a crunched up time here, right? So what you see basically is every time you basically have a step, you have to relearn. And this is sort of the eating at a bad restaurant example. But then you'd get better and better, and over time you do learn, but then you have to have these sort of experiences. Whereas if you have learning, so this phenomenon is known as bursting, and that really has been looked at quite well in the literature. Whereas here you have excitation, you have exploration here, and because of that, your loss function, boom, goes to 0, and your learning error goes to 0. And you no longer see this bursting phenomenon every time you see a new step. And that's the advantage of learning. But this is what you have to make sure that you live with. And bursting, just because your loss function goes to 0 doesn't mean that you have this anomalous behavior. Is something you have to watch out for. And this is what is known as exploration, and which means that when you have a machine learning problem and you have this kind of a scenario, if you don't have the appropriate exploration, you can really have this bursting phenomenon. So something to keep in mind. So I'm going to shift gears now. And now that I've told you a little bit about what adaptation is and what the interconnections are with learning, and what are all the things that we watch out for when we understand the interplay between control and learning, some of the basic tenets are things that have been explored for a long time and explored very well over at length in the field of adaptive control. If you now go on to, okay, now let's talk about, all right, I figured out how to learn the parameter. I figured out how to be robust. What about safety? Because it's not always just making sure that your performance is well behaved. It's also that you stay within a certain step, which means you have to accommodate state constraints, not just input constraints, not magnitude, not just rate, but also that your state should not wander off to some region, should not hit an obstacle, should not enter a stall region. How do you do that and make sure at the same time this can be done? So we've developed an algorithm by an integrative adaptive control where we've been able to take the adaptive controller, which is sitting here, and combine that with ideas from using control barrier functions and appropriately integrate them with some coupling effects here and there. And that basically gives you, so without going into the details, which you can look up the paper, here is an example. So here's a first order example where the whole goal is what you're trying to do is to start here and go here, and without hitting an obstacle, right? Start here, go here. So it's a very simple dynamic system. And we are assuming that there is a loss of effectiveness. So there are parametric uncertainties. So despite that, you want to adapt. And despite that, you want to reach your goal. And despite that, you want to not hit the obstacle. So if you're not careful, if you just take a CBF and integrate it and so on, you can see if what I've done is zoomed in. And when I zoom in that particular region, that is the red rectangle here, the dashed line indicates like a buffer, right? So the actual trajectory is what you see with this sort of magenta color, and it can see that it goes on the wrong side, which is not good. It comes arbitrarily close to the obstacle, which you don't want. So whereas when you introduce this extra component, which again, I won't go into the details of, we are safely away from that boundary and we are on the right side of the buffer and we are able to hit the target. The nice thing about it is all of this is automated. Like, for instance, suppose I tell you there are a whole bunch of other initial conditions that are very, very close to the obstacle. The algorithm automatically figures out the right path in order to get to the target without hitting the obstacle. So which shows that this is actually something that is performs quite well under a variety of operating conditions. We then extended it to a 6-DOF quadrotor where you have, basically a 12-state system. And we introduced a 50% loss of effectiveness in 2 of the 4 motors, again, using this integrative architecture. And so on the left side, you don't have the appropriate integration. So it has CBF, but it has no adaptation. So you can see that it hits the obstacle, whereas on the right side, we are able to start and avoid both obstacles. And you can see that it follows that path, the trajectory that is planned pretty close and without hitting the limit. So, and this is again with a nonlinear quadrotor model with all of the coupling involved. And this is actually a full high fidelity sim using simulating desktop real time. And you'll see the same thing here with, a front end of a validation using VR goggles. And on the left side is basically one where we don't have adaptation. And it's the right side, because of all of the components that are added in, we are actually able to get to that waypoint, which is on the other side of the pillar without hitting the pillar. So all of this basically shows that this is something we can take adaptation and integrate it with these safety-centric ideas of control barrier functions. There's a whole lot of other things that we're doing in relation to this, where we are looking at what happens when you have more lag and you have multiple constraints, and how do you really connect that with optimality. And so those are all the different things that we're looking at. Talking about optimality, now let's jump directly into it. And so when you look at an optimal control problem, we're all not only just talking about minimizing, getting, a performance error, but that performance error is combined with some sort of a cost. So if I have a nonlinear system and then you have a cost, which is some sort of a reward with appropriate discounted structure from all the way from 0 to infinity. And so that's the infinite horizon cost, which means that every time, if you have been optimal at this instant of time and every time before, then what's the additional cost that you have at this when you make a decision right now? And that is the optimal cost to go, which in order to minimize this, we get to the very well-known Hamilton-Jacobi-Bellman equation. So an optimal control policy is basically the one that minimizes this optimal cost to go. Now, if F is unknown, then you have to basically learn this policy, right? So then that basically has led to approximate dynamic programming, which is really what is synonymous with reinforcement learning, right? So what that basically brings in is that if you have a particular policy function or a value function, you have to learn that. You have to learn the mapping, which is where neural networks come in. So the idea behind a neural network is basically that you have some mapping, and this mapping could be this policy or the value function or any other nonlinearity that you're trying to learn. It could be the actual nonlinear control structure, which we know exists, but we don't know what it is, and you're trying to learn that. There could be any number of examples that fits into this kind of problem formulation. And the neural network basically approximates this map, right? So you have, in this particular case, if there's only one hidden layer, this is the structure, this is the activation function. And so the fundamental theorem of universal approximation basically says that, yes, such a neural network exists. And for a certain number of layer of neurons and certain number of weights, then you can show that. And there are all kinds of theorems that have been written, which says that if you have n layers and, so that the learning is embedded in a deep architecture, you can still show that it's equivalent to a single layer, etc. And the actual estimation of the weights occur using backpropagation, right? Which is, again, and that's the one that really connects everything that we've been talking about, which is in the context of a gradient descent, and that gradient descent is then converted into a stability framework, and that gives you guarantees. So you can see that, therefore, many of the ideas from adaptation are obviously linked very tightly with the ideas that have been employed in a neural network. So one can use this neural network, going back to the optimal control problem formulation, that you can approximate all of these things. And you can show that, yes, use an iterative procedure where you collect the data, you collect the corresponding reward, and then for a particular parameterization of that policy using the weights theta k, you can then show that you can solve for what the WK and CK look like from the HJB equation. And then you can use that in turn in order to improve the policy. So, you first, for a given policy, for a given set of weights, then you compute that this is really what the policy looks like. And then you try to improve the policy by adjusting the parameter, and you repeat the whole process. But the problem is basically that this becomes very, very difficult to do. When you have a single layer network with a linear activation function, then we know how to do it. And that's what I showed you in the almost very first slide. Whereas if you have multiple layers, then analytical guarantees become very, very difficult, and it's an ongoing process. But there have been a couple of instances where and there's only 2 examples. There are many more such exist, where people have been able to get these analytical guarantees. So for example, suppose I were to look at a plant. I do know, let's say it's controllable. So you've got the existence of a gamma, which is the nonlinear control policy. But then what you're trying to do is to approximate that. Oops, sorry. And you approximate that using a neural network, right? And what we were able to show was that, how do you train the weights? And in order to make sure that because just coming up with an arbitrary loss function doesn't guarantee that you're always going to remain within a set for which the neural network approximation is valid. So a Lyapunov-centric approach, on the other hand, provides you with that guarantee. And we were able to get that by basically looking at a particular target derivative for the V dot, and use the difference between V and V dot as basically the performance error, right? So it's a very specific loss function that we constructed. We then said we're going to adjust the weight so that this particular J is minimized. And here's an example of what we were able to get out of that. So we picked a very complex nonlinear system where it is simply impossible to figure out through inspection as to what the control policy should be. And so if you use a linear controller, obviously you can stabilize it, but only within a certain region. So a linear controller, therefore, worked fine when the initial conditions were very small, but then for larger initial condition, it blew up. Whereas we were able to bend this linear control policy in the right amount. And this is the difference between the actual linear controller did and what the neural controller did. And that basically gave, for the same initial conditions, it was able to bring it back, which shows that not only analytically we have a guaranteed theorem that says that stability can be delivered, that we also have this particular simulation where it worked. And very similar kind of overall philosophy, but implemented in a very different way, is the safe RL result that was also in the same well-known conference, NeurIPS, but 20 years later. And that was the one that is listed at the bottom. And here, too, the idea is very similar, where you are trying to combine a particular loss function with a Lyapunov function type of level set. And that's what the V of C is in here. And so essentially, the policy that was designed is determined in such a way that it always is keeping all of the state variables inside a level set. And by doing that, they were able to show that this optimal policy can be suitably trained. And this theorem basically says that there is a certain region of attraction, and that region of attraction is guaranteed for this particular nonlinear system, provided the training procedure has elements of this Lyapunov function that are integrated in this particular way. Of course, there's a lot of details, which I will let you peruse at your leisure. But the idea, again, is that one can indeed get these optimal solutions by appropriately borrowing elements from nonlinear optimal control and reinforcement learning. And you have to do it carefully because not oral-based policies are going to give you stability guarantees. So one of the things that we did was basically to exploit the structure between both the leverage the power of RL with adaptive control in the following way. The thing about RL is that there's a lot of offline training, and that offline training basically gives you the policy, right? So that's what we're calling as U sub R. We then said, okay, you can collect all of that and do the offline learning, but then the online adjustments are done using adaptive control. So you have an original policy U sub R, but then you're bringing in all of the corrections to that in the form of an adaptively designed component, drawing from many of the principles that I showed you in the earlier slides. So when we do that, we can actually show that this performance error goes to 0. And there are a lot of details in here as to how the structure should be. You have to construct a particular regressor, and that regressor comes not only from physics-based understanding of the problem, but also from the RL policy itself. So you can see the elements of U sub R and G of XR, which come from the RL. Pn of x comes from the physics, and you need the appropriate coupling term, which is the theta times E. All of that basically gives you a way forward. So I'll just give you a particular example. Remember, I showed you the quadrotor here. I'm going to do the same thing, except that the quadrotor has more specifications, which is that it has to land from arbitrary initial condition, which is inside the box, on this moving platform. And it has to do that within a certain time. So see, these are the additional costs that we are imposing on the problem. It has to do it without moving too much in the XY direction. It shouldn't wobble too much, and you should not have too much of a side velocity or a vertical velocity. And of course, you should not crash, and you should do everything in 10 seconds, right? So it's a complex cost structure, not something that you can always encapsulate in the form of a quadratic cost. And therefore, it's something that becomes really challenging for many of the optimal control methods, right? So we picked that. We then compared it with two different kinds of designs. One is, and both of them with a 50% loss of effectiveness mid-flight, very similar to the video that I showed you. So, and if you do only the RL design where you don't accommodate the fact that you have any kind of stability guarantee, then it turns out that it actually crashes. And on the right side is the video that corresponds to the simulation where you have adaptive control that also is introduced in the inner loop. And when we do that, we can actually not only accomplish the stability goal, but you can also accomplish that in the time that was specified. And you can see the performance comparison here, where we change the loss of effectiveness all the way increase it from 0 to 75%. So this is something that shows that, there is a way in which you can combine adaptation with optimality-based principles and accomplish that objective. And the reason why this adaptive control is needed is because the model that the RL has been trained for is inadequate. So you can see that when you have a 50% loss of effectiveness, which is what these figures correspond to, in the vertical direction, the Z dot basically is the one that RL thinks it is along these lines and is fashioning its policy based on that. Whereas the reality is that it's further and further away. And therefore, at some point, whatever it was trained for and what the actual system is depart quite a bit, and therefore it's not able to guarantee a good performance. And that's the reason why we are able to do better. We've also sort of extended this idea for an LQR that is obviously an optimal controller, but then how do you then figure out what it should be when you have uncertainties? And so let me just give you a quick example through these slides. So the way in which adaptive LQR works is that you have a plant, and the plant basically has input and output is subject to some noise, and here's a controller. So what you do is that then the whole problem is basically that A star and B star are the dynamics, and it's unknown, right? And if I don't know A star and B star, I want to be able to still come up with an optimal policy. So what do? So then I collect the data, and then I estimate the A star and B star, and then I make sure that my information matrix is full rank. And so once I have that, then I basically say, okay, I have new estimates, and I use the new estimates to calculate the feedback gain. And this is your adaptive LQR, right? So the difficulty, there are many challenges here. You have to collect data for a while. And if you're collecting data for a while, your controller is still using the old A star, B star, right? So that means whatever your initial controller is you put in better be stabilizing. So you should have, even though A star, B star is unknown, you should have enough information about it to design a game. That's the problem, right? So the initial controller must be stabilizing. So that's the challenge. The next thing is, what if it isn't stabilizing? Then you have a problem, right? Then we need excitation to learn very quickly and stabilize. And so stability relies, however, on excitation. So then there is some sort of a feedback, right? So, and not only that, then what you try to do is whenever you try to search for a better set of parameters, then the optimization that you have to perform is very difficult. So all of these things basically introduces challenges. And so can we develop an algorithm that doesn't require any of them? And we have a result that says that, yes, you can. And the way we do that is to have a slightly different parameterization for the adaptive controller based on a direct approach. And this G hat and K hat is designed in a very specific way. And we have basically a recursively squares-based adaptive algorithm that computes this. And we basically adjust that K hat, G hat directly instead of computing A hat and B hat and using that to calculate the control parameters. And every time we basically use this exploration data, and then we have a full rank information matrix, we then calculate not K hat, B hat, G hat directly, but a new reference model. So this new reference model gives you the right target, and then we repeat the whole process. So this is really what we do. And the nice thing about it is that it also gives you an additional advantage of having robust learning, because when you have unmodeled dynamics, this kind of a learning basically gives you a way of not only coming up with an adaptive optimal LQR, and so as opposed to existing literature, which basically uses persistent excitation from the Gaussian noise and estimates A hat, B hat, our algorithm uses spectral lines and some Gaussian spectral lines to come up with a better deterministic input with the right frequency content that doesn't excite unmodeled dynamics. And this allows us to actually give a guarantee of robustness when unmodeled dynamics is present. And so when you explore this particular dynamic system where we had marginally stable Laplacian dynamics, the design that we got with our approach basically gave us a much smaller state magnitude. And when we applied it to the 6-DOF quadrotor example that I showed you, our algorithm again gives you a much smaller, a much better performance error and is more optimal compared with some of the other methods that use this Gaussian noise. And this is what happens with unmodeled dynamics. So those are all the different things that I wanted to share with you. Well, okay, sorry, to just give you a little bit more information in here. When you have no unmodeled dynamics, the Gaussian noise exploration and our method basically perform, so that's what you see at the top. Whereas what you're seeing at the bottom is with unmodeled dynamics, and you can see that our regret basically is much, much smaller than what the Gaussian exploration does. And this is with two different kinds of signal noise to signal ratio. The one on the right side is much higher, and you can see still that our algorithm outperforms. So this is really what I wanted to share with you. I hope I was able to convey to you the basics of adaptation and how all of adaptation is integrated, is firmly in sync with learning. And because all of them really are built on top of parameter learning, but we always were also worry about imperfect learning, noting that learning of parameters is a much more complex task than just performing a control goal. We are able to integrate it with a whole bunch of other systems properties that any safety critical system must have, including safety and optimality. And I hope I was able to show you some of the examples of how to do that using the quadrature example as well as the adaptive LQR. So in general, this is really where we are taking this whole story to in our lab, that we are developing these adaptive control architectures that's really capable of these fundamental systems properties that learn, that deliver high performance and make sure that things are safe and do all of that in an optimal manner. When you've got uncertainties or environmental changes, or when there are the other kinds of state constraints on the problem that can be significant. And so, in all of these things, I think one has to make sure, especially in the context of a real-time control, what kind of time scales do we have in the problem? Because in some cases, you just really need to adapt first. Otherwise, you're going to always have this recursive problem or tautology of, oh, I need to pick the parameters. Oh, I need to make sure that it's stable, but you don't know the parameters, et cetera. And so sometimes you just need to adapt first. And guarantees with imperfect learning are essential. Learning is something that really only comes with excitation, or exploration comes with hindsight. So we really do need to move towards fully autonomous systems, which means we have to have these decision-making tools with guarantees. We have to integrate with other building blocks. And sometimes you do need to address control for learning. It's not always learning for control, because you need to make decision-making sometimes under fast timescales. There are all these papers that my presentation here was built on, and I would refer you to all of those papers for further reading. And I'd like to thank you very much for your attention.
Thank you so much, Dr. Annaswamy. We can take any questions right now if there are. And before people ask questions, when you mentioned this thing about the parameters need to be, or the control has to be excited before, in order for you to learn them and then be able to have the sort of a trade-off between optimality and that sort of thing. So I'm just wondering, in reinforcement learning, when it comes to offline reinforcement learning, there are if you consider safety critical systems, you may not have the luxury to explore certain regions, and you might only be restricted to what you have. And how should one go about guaranteeing, let's say, could you perform the best within what has been explored, and all of these things in this sort of a combined framework?
Right. So that's the thing where the analytical guarantees that I mentioned really come into play. So if you really have not had the opportunity to go to certain regions at all during your exploration, then if for whatever reason a disturbance or some anomaly comes in that takes you to those regions, then you've really not trained the neural network, right? So you need to have some kind of buffers or some kinds of guardrails to make sure as to how you bring your system back. So the two papers that I showed you are just examples of how you can circumvent that. So that's the reason why you don't have, we start with some loss functions, then you introduce some intersections with some of the level sets that you get from a Lyapunov function, or in the first paper that I mentioned, it's completely based on, that loss function is completely based on how far the actual Lyapunov derivative is from where you want it to be. So that is some guardrails like that are certainly needed. But there's always a trade-off. training the system with those kinds of cost functions, modified loss functions, are extremely hard to do. If you don't know what you're doing, it can take up to a year to train some of these things. So that's always the problem. So you hope, that's why, when you have the offline exploration, you really take it through all possible data so that you avoid some of these. So PPO, which performs extremely well, essentially tries to do that using all of these different actor-critic methods and so on, that somehow makes sure that cleverly it samples the space that you need to sample in order to make sure that you are able to bring things back quickly from where you're departing. So
Yeah.
I think some of those guardrails are essential in order for us to go forward.
Okay. Yeah. Thank you so much. Let me check if there are questions from the stream. Yeah, I think we don't have any questions from the stream yet, but maybe they can direct some questions to you if
Of
they need
course.
to or
Sure,
something.
absolutely.
Thank you so much. Yeah, thank you so much for speaking at our seminar series, and it was really fun to understand how you draw parallels with adaptive control and reinforcement learning, and
Thank
yeah,
you.
it was very insightful. Yeah, thank you so much.
Thank you. My pleasure. And again, thank you for the invitation, and it's a pleasure.
Thank you so much.
All right. Thank you,
Yeah,
Nishant.
all right.
All right. Bye.
Bye bye. All right, everyone. This is the end of DDLC seminar series for this semester, and the next talk will be the spring 2025 semester. It's on the January 23rd, and I will send out a reminder in due time so you could be on top of that. Thank you so much for listening to this talk, and until next time, see you.